Hello everyone. Today in this video I will read chapter Atomic Structure of Modern Book. So let's get start. So first of all there is a topic de Broglie concept of matter waves. Einstein in 1905 suggested that light is a dual nature. It can be behaved as a particle as well as wave. It was observed that some of the experimental facts regarding light, such as reflection, refraction, dispersion, interference, etc., could be explained only by assuming light to have wave-like character. With some other experimental facts, such as black body radiation, photoelectric effect, etc., could not be explained by assuming particle-like character for light radiations. When an electron was discovered, the various experimental characteristics it showed that an electron behaves as a particle. In Bohr's theory, electron is treated as a particle. However, in 1924, Louis de Broglie suggested that just as light exhibits wave and particle properties, all microscopic materials, particles in motion such as electrons, protons, atoms, ion, molecule, etc. have also dual character. In other words, the microscopic particle in motion possesses both the particle and wave characteristic. Thus, according to de Broglie, all particle in motion possesses wave characteristics. According to de Broglie, the wavelength associated with a particle of mass m and moving with a velocity v is given by the relation lambda is equals to h divided by mv, or lambda is equals to h divided by p, where h is Planck's constant and mv or p is the momentum of the particle. The waves associated with material particle are called matter waves. Derivation of de Broglie relationship. The relationship may be derived by combining the mass energy relationship proposed by Max Planck and Einstein. According to Planck's photon of energy, light energy, E is associated with the wave frequency mu as E is equals to h nu. According to Einstein, mass and energy are related as E is equal to mc square, where c is the velocity of light. Combining the above four relations in equation 2 and 3, we will get h nu is equal to mc square. Now, since mu lambda is equal to c, or mu is equal to c by lambda, therefore hc by lambda is equal to mc square. Cancelling c, h divided by lambda is equal to mc, or lambda is equal to h divided by mc. This equation is valid for a photon. The next step was taken by de Broglie, who realized this wave particle duality is not necessarily unique to photon but may also be exhibited by other microscopic particles such as electron. He therefore suggested that on substituting the mass of particle m and its velocity v in place of velocity of light c, the equation can also be applied to material particles. Thus, the wavelength of material particle lambda is equal h divided by m. This equation is known as de Broglie equation and explain dual nature of matter. The matter with mass m and velocity v, properties associated with particles, has a wavelength lambda, a property associated with waves. Therefore, while all matter in motion would have an associated waveform, but the wavelength is only meaningful when m is small. Justification for the dual nature of electrons. The particle and wave nature of electron can be justified on the basis of the following observation. First is particle nature. Electron exhibits the characteristic of particles. They have definite mass and energy, momentum and charge. When an electron strikes a zinc sulfide screen, it produces spot of light known as scintillation. It has been observed that each striking electron produces only one scintillation point. This indicates that the scintillation and therefore the striking electron must be localized and not spread out like a wave. This suggests that the electron behaves as particle. Second is wave nature. The wave nature of electrons was experimentally verified by Davison and Gummer in 1927 and George Thomson in 1928, who observed diffraction of electron by crystals. Now, quantum numbers. Quantum numbers were earlier proposed by Bohr as number required to specify the position and energy of electron in an atom. In wave mechanics, when Schrödinger wave equation was solved for hydrogen atom, it was observed that the electron in an atom can be characterized by a set of three numbers known as quantum numbers. These are designed as n, l and m. In addition of these three numbers, another quantum number is also needed to specify the spin of the electron. This is designated as s. These are discussed below. First is principal quantum number n. This quantum number determines the mean energy level which an electron occupies. This is represented by the letter n. It can have integral value started from 1, that's n is equals to 1, 2, 3 up to. This quantum number is also regarded as shell. The shell with n1 is called the first shell. The shell with n2 is called the second shell, and so on. The various shells are also identified letters breaking with K for the first shell n is equals to 1 as given ahead. This quantum number n determines the energy of the electron according to the formula En is equals to minus 2 pi square m e to the power 4 n divides by n square h square is equals to minus 2.18 into 10 to the power minus 18 divided by n square joule per atom, or minus 1311.8 n square kilojoule per mole. For example, the energy of the electron in K shell n is equals to 1 is equals to 1311.8 kilojoule per mole negative. As like we can find energy of E2, Nz2, E3 and E4. Now it shows that the value of n increases, the energy of the electron in that shell also increases. The principal quantum number also helps to determine the average distance of the electron from the nucleus and its energy. For n is equals to 1 first cell, it represents the energy level nearest to the nucleus having lowest energy. Thus, as the value of n increases, the average distance of electron from nucleus increases and also the energy of the electron in that shell increases. It may be noted that theoretically there is no limit to the number of shells value of n, but 7th cell is the highest cell occupied by the known elements. Second is azimuthal or subsidiary quantum numbers. This quantum number gives this subshell or sublevel to which an electron belongs. It designates L, and corresponding to each value of n, there are n possible values of this quantum number ranges from 0 up to n minus 1. This is the possible value of Lr. L is equal to 0, 1, 2, 3 up to n minus 1. This quantum number gives the energy of the electron due to angular momentum of electron. The angular momentum of the electron is related to L as angular momentum is equal to h divided by 2 pi into under root L into L plus 1. Each value of L represents a particular subcell or sublevel. The value of n determines the possible value of L. When n is equal to 1, L can have only one value, that's 0. This means that there is only one subshell, that the subshell and shell are really identical. When n is equal to 2, L can have values 0 and 1. This means that in the second shell there are two subshells. When n is equal to 3, L can have three values 0, 1, 2. This means that there are three subshells in third shell. Therefore, each value of n, there is value of n. The different values of L are designated by the letter S, P, D, F, and G. The S, P, D, and F, G designation arises from characteristics of spectral lines produced in spectra. S for sharp, P for principal, D for diffuse, and F for fundamental. For L is equal to 4 and higher values, the designation follow alphabetically order. After F, that's L is equal to 4, is designated as G. L is equal to 5 is designated as H, and so on. To designate a particular subshell, we write the principal quantum number n is equal to 1, 2, 3 up to, followed by the letter designation for the value of S, P, D, F. For example, subshell with n is equal to 1 and L is equal to 0 is denoted as 1s. A subshell with n is equal to 3, L is equal to 2 is denoted. Now, third is magnetic quantum number. This quantum number describes the preferred orientation of the electron in the presence of magnetic field. An electron is a charged particle and is moving around the nucleus. The movement of electron is similar to the flow of an electric current through a loop will therefore generate a magnetic field. When external magnetic field is applied, the magnetic field due to flow of electrons will interact the external magnetic field. As a result, the electron in a given subshell may take several orientations with respect to applied magnetic field. These orientations or regions of space are called orbitals. The number of these orientation in space orbitals is given by the magnetic quantum number is designated by m. The value of m depends upon the value of L. For a given value of L, m values ranging from minus L through 0 to plus L. That's m is equal minus L 0 to plus L. For example, if L is equal to 0, m can have only one value 0 because positive and negative 0 are the same. Thus, as a subshell, L is equal to 0 has only one orbital. If L is equal to 1, m can have values minus 1, 0, plus 1. That's 3 values. This means that P shell can have 3 orbitals corresponding to values L is equal to 1, m is equal to minus 1, and L is equal to 1. M is equal to 0, L is equal to 1, and m is equal to plus 1. This means that a P subshell can have 3 orbitals, namely Px, Py, and Pz. These orbitals are degenerate by this degeneracy in split up in the presence of magnetic field as shown in the figure. Similarly, if L is equal to m can have values minus 2, minus 1, 0, plus 1, plus 2, fine values. This means that D subshell can have 5 orbitals. The 5 orientation of angular momentum in external magnetic field for L is equals to are shown in figure 7b. Similarly, it can be shown that F subshell can have 7 orbitals. The orbitals in F subshell are given below. The number of orbitals in a subshell are easy to remember because they follow simple arithmetic progression. Thus, there are 2L plus 1 orbital corresponding to each value of L. The relationship among the values of N, L and M are given in the table 1. From the above table, it is clear that the number of orbitals in a given shell is n square. The different orbitals corresponding to different values of m have different designation. For example, for L is equal 0, m is equal 0, it's s orbital. For L is equal 1, m is equal minus 1, 0, plus 1, the three orbitals are designated as px, py and pz. As like for L is equal 2, the 5 orbitals are designated as dxy, dxy, dyz, dzx, dx square minus y square and dz square. As like f x cube, fy cube, fz cube, fxyz, fx into z square minus y square, fy into x square minus z square, and fz into y square minus x square. Now, the fourth is spin quantum number. The quantum number did not originate during the solution of Schrödinger wave equation, but it was introduced to account for the spin of the electrons. It has been observed that the electron is not only revolving around the nucleus but also spinning around its own axis. The spinning of electron will generate magnetic field in addition to orbital motion of the electron. The quantum number describes the spin orientation of the electron and is designated by S. The electron can spin in either of the two directions, clockwise and anti-clockwise. It has been shown that S can have the values plus half and minus half. The plus and minus signs may be thought as arising from the direction of the spin, clockwise or anti-clockwise. Therefore, an electron besides charge and mass has also spin angular momentum, commonly called spin. The spin angular momentum of an electron is constant and cannot be changed. The magnitude of spin angular momentum of an electron is given as spin angular momentum is equals to under root s into s plus 1 into h divided by 2 pi. For example, for spin quantum number s is equal half, then spin angular momentum is equals to under root 1 by 2 into 1 by 2 plus 1 into s divided by 2 pi. This will be equals to under root 3 by 4 pi into s. Now, Pauli exclusion principle. After setting the rules for the possible values of quantum number, we can calculate the maximum number of electrons that can be added in each shell and subshell in atom. For this, there is a guiding principle known as Pauli exclusion principle. This principle can be easily understood. We have learned that an orbital is specified by three quantum numbers n, l and m. Since an electron in an orbital must have same values of n, l and m, it follows that it can have two values as either positive half and negative half. In other words, an orbital can have at the most two electrons provided in their spin quantum number are different. For example, consider K shell where n is equal 1. It will have only one value of L as L is equal 0 and one value of M as M is equal 0. It can be have either of the two values of S as positive half or negative half. That's n is equal 1, L is equal 0, M is equal 0, then S is equal to positive half. If n is equal 1, L is equal 0, M is equal 0, then S can be negative half. This tends to the conclusion that an orbital can have maximum of 2 electrons. Moreover, if an orbital has 2 electrons, they must be of opposite sign. Thus, Pauli's exclusion states that an orbital can contain maximum of 2 electrons. Similarly, it can be calculated that S subshell can have max of 2 electrons. P subshell can max have of 6 electrons. D subshell can max have of 10 electrons and F subshell can have max of 14 electrons. It may be noted that the number of electrons in a subshell does not depend upon the value of principal quantum number. From this, we can calculate the number of electrons in various shells as given ahead. Now, electronic configuration of atom. The distribution of electron in different orbital is known as electronic configuration. The electronic configuration of an atom is written by filling electrons in various orbital one at a time and by placing each new electron in the lowest available orbital. An atom in its low energy state is said to be in the normal state or the ground state. For the sake of presentation, the following symbols are commonly used. A box for an orbital, square or circular, or an arrow for an electron. The direction of the arrow giving the orientation of its spin. Two arrows are shown for two electrons with opposite orientation of spin. Alternatively, electronic configuration is expressed by indicating the principal quantum number and its respective orbital along with the number of electrons present in it. For example, the notation of 3px1 indicates that there is one electron in px orbital of third principal shell. The filling of orbital is governed by the following rules. First is Aufbau principle. The Aufbau principle, the word Aufbau is a German word which means building up, is the procedure for filling of orbitals with electrons. It states that in the ground state of an atom, an electron enters the orbital of lowest energy, first and subsequent electron are fed in the orbital increases energy. For an energy level diagram, figure 3.1, for multi-electron atoms, the following sequence is observed for orbital in the increasing energy: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4d, 5d, 6p, 7s. According to Auer principle, the orbital should be filled in the above sequence. It's important to remember that the sequence of energy level pertains up to 3p and then 4s orbital first instead of 3d. In fact, the energy of an orbital is determined by the number n quantum number n and l with the help of important rule known as n plus l rule or Bohr-Bree rule. According to this rule, in neutral atoms, the orbital with lower value of n plus 1 has the lowest energy, and if the two orbitals have the same value of n plus L, then the orbital with lower value of n has lower energy. For example, 3s orbital n plus L is equal 3 plus 0 equal 3 possesses lower energy than 3p orbital. 2p orbital and 3s orbital have the same n plus value, but 2p orbital have lower value of n and therefore is lower in energy than 3s orbital. This rule helps us to account for the fact that certain orbital with higher value of n but lower value of L have less energy than orbital with lower value of n and higher value of L. For example, let us apply this rule to 4s and 3d orbital. For 3d orbital, n plus value is equals to 5, while for 4s orbital, n plus value is equals to 4. Thus, 4s orbital has lesser energy than 3d orbital. The difference in energy of the various subshells of the same shell arises due to difference screening of the inner electron, resulting in different effective nuclear charges experienced by the outer electron occupying a particular subshell. Higher the effective nuclear charge experienced by an electron present in a particular shell, the greater will be the nuclear attraction experienced by it, and therefore lesser will be the energy of the subshell. This has already been explained on the basis of Slater's rule. It has been shown that after 3p6 configuration, 4s subshell has lower energy than 3 the subshell. Therefore, the last electron in potassium will go into 4s orbital rather than 3d orbital. The sequence of energy level can be easily remembered by the following systematic diagram. Quantitatively, the order of energy of various orbitals can be easily explained from the radial probability distribution curves. Second is Pauli exclusion principle. According to this principle, an orbital can accommodate maximum 2 electrons and these 2 electrons must be of opposite spin. The principle thus limits to the accommodation electron in an orbital. This means that an orbital can have 0, 1 and 2 electrons. Moreover, if an orbital has 2 electrons, they must be of opposite spin. The principle has already been discussed. Third is Hund's rule of maximal multiplicity. According to this rule, electron pairing will not place in orbitals of same energy, same subshell until each orbital is singly filled with parallel spin. In other words, in a set of orbitals having same energy, degenerate orbitals, the electrons distribute themselves to have parallel spin as far as possible. This rule can be illustrated considering the example of carbon. The atomic number of carbon is 6 and it contains 2 electrons, the 2p subshell, and these can be distributed in the following 3 ways. Since all the 2p orbital have same energy, therefore it does not make any difference as which of the 3 orbital contain electrons. In state 1, both the electrons are in the same orbital. In state P, the t electrons are present in different orbital but with opposite spin, while in state C, the electrons are present in different orbital with same spin. Now the electrons are charged particle and they repel each one another. The electron-electron repulsion are minimum when the electrons as far as apart as possible with parallel spin. The state C has minimum repulsion and correspond to lower energy stable state. This is also in accordance with Hund's rule. Similarly, the electronic configuration of nitrogen may be represented as when the shell become half filled, that's all the orbital of all the subshell get singly filled, the successive electrons being to pair up in these orbitals. Thus, the Hund's rule may be summed up in the following 2 rules. First, in the orbital of same energy like 2px, 2py, 2pz, the electron pairing will not occur unless each orbital is singly filled. When 2 electrons are filled in different orbital of same energy, their spins should be parallel. Then, this principle is very important in guiding the fill of p, d and f subshell which have more than one kind of orbitals. This becomes further clear when we write the electronic configuration of different atoms as discussed below. Effective nuclear charge and Slater's rule. As already discussed, in multi-electron atom, the electron in the outermost shell are screened from the nucleus by the inner electron. As a result, the electron in the outermost shell not experience the full charge of the nucleus. The actual nuclear charge felt by electron is called the effective nuclear charge. For example, an electron in outermost 2s orbital 2s1 does not experience the full charge of nucleus because there is an intervening shell or core of first 1s2 electron. The effective charge felt by this 2s1 electron, known as the effective nuclear charge, will be less than the actual nuclear charge. This means that the various inner orbital electrons clouds serve as a screen between the nucleus and the outermost electron. Therefore, the outermost electron does not experience that much attraction from the nucleus which it would have experienced if there were no intervening electrons. So, the inner electrons shield or screen the outermost electron. This is called the shielding effect or screening effect. The effective nuclear charge can be determined by subtracting a screening constant for inner electron from the actual nuclear charge atomic number. Thus, the effective nuclear charge Z star experienced by an electron may be expressed as Z star is equal to Z minus S, where Z is equal to nuclear charge equal to atomic number and S is equal to shielding constant, or can say screening constant. The screening constant S is a measure of the screening contribution of all the other elements in an atom. Electron in an atom. Obviously, if screening is small, the effective nuclear charge will be high, and if screening is large, the effective nuclear charge is low. Slater proposed certain rules calculating for the effective nuclear charge. These rules are known as Slater rules. Slater rules has proposed certain rules to calculate the screening constant for electron in different shell. From the knowledge of screening constant, the effective nuclear charge is calculated by subtracting it from the nuclear charge. This Slater rules. Write the electronic configuration of the element in the following order and group: 1s 2s 2p, 3s 3p 3d, 4s 4p 4d, 4f 5s 5p, and 5d and 5f. In this grouping, the s and p orbital of a shell, same value of L, are written together, while d and f orbital are written separately. Second is, electron in any group higher in the sequence than the electron under consideration screen those in lower group and therefore contribute 0 to this screening constant. Electrons in the same group contributes S is equal to 0.35 each. It may be noted that for 1s electron screening another 1s electron, the screening constants for an electron in ns or np orbital, all electrons in n-1 shell contributes S is equals to 0.85 each. All electron in deeper shell, that's n-2 and lower shell, contribute S is equals to 1.0 each. For an electron in nd or nf orbital, all electron in the lower group contribute S is equal to 1.0. It may be noted that in case of nd or nf electron, the electron in all the lower groups, even having the same value of n in same shell, contribute S is equal to 1.0 each. For example, by calculating screening contribution for one of the electron in 4d group, the electron present in 4s 4p group having same value of n, that's 4, contribute S is equal to 1.0 and not 0.35. Only the electron present in the same 4d group will contribute 0.35. The shielding constant as obtained from the sum of the contribution as explained above is subtracted from the nuclear charge Z to obtain the effective nuclear charge Z star, affecting the selected electron. To illustrate this application of Slater rule, let us consider few examples. Now, I will read the concepts which are related to the periodic table. So, let's start. Modern periodic law. In 1912, Moseley shows that the physical and chemical properties of the atoms of the elements are determined by their atomic numbers and not by their weight. This acceptance of the atomic number as the important characteristics of an atom in the modern periodic law, which may be stated as the physical and chemical properties of the elements are periodic function of their atomic number. Consequently, when the elements are arranged in order to increasing their atomic number, it is observed that the elements of similar properties recur at regular intervals or periodicity. As a result of this, the elements fall in certain group and lead to an arrangement called the periodic table. With the modern periodic table lies the guiding principle. Many new forms of the periodic table have been proposed. However, the general plan of the table has remained the same as proposed by Mendeleev. Of these, the most commonly used form is known as long form of the periodic table. The long form of the periodic table, position of elements in the periodic table. Periods. A horizontal row in the periodic table is called periods. In terms of electronic structure of the atom, a period constitutes a series of elements whose atoms have the same number of electron shell, that's principal quantum number, and there are 7 periods and each period starts with a different principal quantum number. Groups. A vertical column in the periodic table is known as group. In terms of electronic structure of the atom, a group constitutes a series of elements whose atoms have the same outermost electronic configuration, but they have different number of total electrons. There are 18 groups in the long form of the periodic table, according to the new recommendation of the International Union of the Pure and Applied Chemistry (IUPAC). The groups are numbered from 1 to 18. Previously, these were numbered only from 1 to 8 as A and B groups. Both the system of numbering the groups are given the periodic table. However, the old convention is still used in many books. The recurrence of similar properties of the element after certain regular intervals when they are arranged in order to of increasing atomic number is called periodicity. The classification of the elements in certain families was based upon the observed similarities in the physical and chemical properties. But why do these certain elements exhibit similar properties, and why do similar properties recur at regular intervals of atomic numbers? Where some important question yet to be answered. We know that an atom consists of nucleus surrounded by electrons. In ordinary chemical reaction, the nuclei of the atoms don't undergo any change, and therefore it is the distribution of the electron in the various shell of their atoms that determine the physical and chemical properties of the element. Further, it has been also found that the properties of atoms don't depend so much on the arrangement of electron in the inner shells. Thus, it must primarily be the arrangement on the arrangement of electron in the inner shell. Thus, it must primarily be the arrangement of electron in the outermost shell called the valence shell that determines the properties of the atom. For example, the electronic configuration of the atoms of alkali metal group, table 2, shows that they all have one electron in the s orbital of the outermost valence shell, preceded by the noble gas configuration ns2 np6, but for lithium ns2. The general electronic configuration of these may be written as noble gas ns1, where n stands for principal quantum number. Thus, the cause of periodicity of the properties of element is the repetition of similar electronic configuration of their atoms in their outermost shell, energy shell, or valence shell after certain regular intervals. Periodic properties. There are many physical and chemical properties of element which show periodic variation with atomic number. Some of these properties, such as valency, atomic size, ionization energy, and electron affinity, are directly related to the electronic configuration of the atom, while some properties such as melting point, density, etc., are indirectly related to the electronic configuration. Atomic radii is very important property because many physical and chemical properties are related to atomic radii. Generally, the term atomic radius means the distance from the center of the nucleus of the outermost shell of electrons. If the atom is assumed to be spherical, it is the radius of the sphere. However, the absolute size of an atom is difficult to be defined because of the following reasons. According to the probability picture of electron, an atom does not have well-defined boundary. The probability of finding the electron is never zero, even at large distances from the nucleus. It's not possible to isolate an atom and measure its radius. The probability distribution of an atom is also affected by the presence of the other atom in its neighborhood. Therefore, the size of atom may change in going from one set of environment to another. Thus, we can arbitrarily define atomic radius is the effective size, which means the distance of closest approach of one atom to another atom in a given bonding situation. In other words, atomic radius corresponds to the limit of approach of another atom in a particular substance. Therefore, the atomic radii may be called as covalent radius, van der Waals radius, ionic or crystal radius, depending upon the types of bonding. Covalent radius. The radius of an atom is calculated by measuring the distance between the center of two atoms, internuclear distance in molecules, with the help of X-ray diffraction or spectral studies. In case of homonuclear diatomic molecules, the atomic radius is defined as one half of the distance between the center of the nucleus of two similar atoms bonding together in a molecule. The radius is called as covalent radius because the atoms in a homonuclear diatomic molecule are held together by covalent bond. For example, the intermolecular distance between the two atoms of in H2 molecule is 0.74 angstrom. Second is metallic or crystal radius. This gives the size of the atom in case of metallic element. In case of metal, a large number of atoms are closely packed and are held together by means of metallic bonds. The close packing of the metal ions is known as crystal lattice or metal lattice, and this packaging is different in different metals. The metallic radius may be defined as one half of the distance between the nucleus of two adjacent atoms of a metal in a metallic lattice. The internuclear distance between the nearest neighboring atoms in a metallic crystal determined by X-ray diffraction. This is divided by 2 to calculate the metallic radius as R metallic is equal to internuclear distance between the two adjacent atoms in metallic lattice divides by 2. Third is Van der Waals radius. Van der Waals radius is defined as one half of the internuclear distance between the adjacent atom belonging to the nearest neighboring molecules of the same substance in the solid state. Radius, van der Waals radius is equals to internuclear distance between two non-bonded nearest neighboring atoms divided by 2. Now, periodic strands in size. First is variation of atomic radii in a period. In general, the atomic radii decrease as we move from left to right in a period in the periodic table. Explanation. This may be explained on the basis of increasing nuclear charge along a period. With increase in atomic number from lithium to fluorine, the magnitude of the nuclear charge increases with the corresponding addition of electron takes place in the same principal shell. Second, since the electrons in the same shell don't screen each other from the nucleus, the increase in nuclear charge is not neutralized by the extra valence electron. As a result, electrons are pulled closer to the nucleus by the increased effective nuclear charge and thereby cause a decrease in the size of the atom. In this way, the atomic size goes on decreasing across the period. Second is variation of atomic radii in a group. The atomic radii of element increases from top to bottom in a group. Explanation. In moving down a group, the nuclear charge increasing with increase in atomic number and we expect that the size of atom should decrease. However, while going from one atom to another, there is an increase in the principal quantum level. Although the number of electrons in the outermost shell remains the same, the effect of increase in the size of the electron cloud is more pronounced than the effect of increased nuclear charge. Consequently, the distance of the outermost shell electron from the nucleus gradually increases down a group. In other words, the size of atom goes on increases as we move down in a group. Ionization energy. Ionization energy of an element is defined as the amount of energy required to remove the most loosely bounded of electron from an isolated gas state. Ionization energy is also called an electronic potential. It is expressed in the term of either kilocalorie per mole or kilojoule per mole or electron volt per atom. Thus, the ionization energy gives the ease with each electron can be removed from an atom. Evidently, the smaller the value of ionization energy, the easier it is to remove the electron from the atom. Factors on which ionization energy depends. First is size of atom. The attractive force between the electron and the nucleus is inversely proportional to the distance between them. Consequently, as the size of the atom increases, the outermost shell electron are less tightly held by the nucleus. As a result, it becomes easier to remove the electron and therefore ionization energy decreases with increase in atomic size. Second is charge on the nucleus. The attractive force between the nucleus and the electron increases with increase in nuclear charge. Therefore, the increase in nuclear charge, it becomes more difficult to remove an electron and ionization energy increases. Third is screening effect of the inner electrons. In multi-electron atoms, the outermost electrons are shielded or screened from the nucleus by the inner electrons. This is known as the shielding or screening effect. As a result of this, the outermost shell does not feed the full charge of the nucleus. The actual charge felt by an electron is termed as effective nuclear charge. Effective nuclear charge is Z effective is equal to total nuclear charge Z minus screening constant S. And increasing the number of electrons tends to decrease the ionization energy. Fourth is penetration effect of electrons, and fifth is electronic arrangement. Now, electron affinity. Just as energy is required to remove an electron from an atom, energy is released when an electron is added into a neutral atom. This is called electron affinity. Thus, the amount of energy released when an electron is added to an isolated gaseous atom is called the electron affinity. Electron affinities can be positive or negative. When energy is released during the addition of an electron to an atom, the electron affinity is taken as positive. Electron affinity are expressed in kilojoule per mole. Factors on which electron affinity depends. First is nuclear charge. The electron affinity increases as the nuclear charge increases. Second is size of the atom. With the increase in size of atom, the distance between the nucleus and the incoming electron and to increase and the result in lesser attraction. Consequently, the electron affinity value will decrease. Third is electronic configuration. The elements having stable electronic configuration of half and completely filled valence subshells show very small tendency to accept additional electrons, and thus electrons affinities are low or almost zero in certain cases. Periodic trends. Electron affinity is general, increases from left to right in a period and decreases from top to bottom in a group. Halogens have the highest electron affinities. The electron affinity of the halogen group are the highest. This is due to the fact that halogen have the general electronic configuration of ns2 np5 and have only one electron less than the stable noble gas configuration. Thus, they have strong tendency to accept an additional electron and the electron affinities are therefore high. Electron affinities of noble gases are zero, while those of magnesium, nitrogen, phosphorus are almost zero. The electron affinity of noble gases are zero. This is because they have stable electronic configuration of ns to np6, thus they have absolutely no tendency to take an additional electron. This means that the incoming electron does not feel any attraction of the nucleus. Thus, no energy released in their electron affinities are zero. Similarly, the low, almost zero electron affinity value for beryllium, magnesium, nitrogen, and phosphorus can be explained due to extra stability of fully filled 2s and 3s orbital respectively, and of half-filled 2p and 3p orbital of n and p respectively. Therefore, the configurations show little tendency to gain an electron, and hence their electron affinities are almost zero. Electron affinity of fluorine is unexpectedly less than that of chlorine. The low value of F atom is due to very small size of the F atom. As a consequence of small size, there are strong inter-electronic repulsion in the relatively compared 2p subshell of fluorine, and thus the incoming electron does not feel much attraction. As a result, its electron affinity value is small. On the other hand, the electron affinity of fluorine atom is larger than fluorine atom, while the electron is added to a relatively large 3p orbital, which can be easily accommodate the addition electron. Electronegative. When a covalent bond is formed between two homonuclear, the shared pair covalent bond lies exactly midway between the nuclei of the two atoms because of they may have same attraction for these electrons. For example, in molecules such as H2, Cl2, F2, electron pair remains exactly at half distance between the two nuclei. However, in the case of covalent bonds between dissimilar atom, heteronuclear molecules, the electron pair may be closer to one another than to the other. This is due to the fact that different atoms have different tendency to attract the bonded pair of electron toward itself. The tendency of an atom is to attract the shared electron pair in a molecule itself is called electronegativity. Different atoms have different tendency to attract the bonding electron pair towards themselves. Greater the stability of an atom to attract electron in a bond, larger is the value of its electronegativity. It must be remembered that unlike other atomic properties such as ionization and the electron affinity, which are related to the individual gaseous atoms, the electronegativity is related to the atom in their bonded state. There is no direct method of measuring the electronegativity. However, various attempts have been made to drive a scale of electronegativity for the elements. Some of these scales are discussed below. First is Pauling scale of electronegativity. If two atoms A and B had the same electronegativity values, the bond energy of A and B would be equal to the geometric mean of the bond energy AA and BB molecule. For example, the bond energy of AB molecule may be written as EAB is equals to EAA into EBB under root. The relation is based on the assumption of poor covalent bond in A2 and B2 and AB molecule. However, he observed that for the most of the AB bonds, the actual bond energy is more than the geometric mean of bond energy of EA and EB. In other words, the bond A and B will no longer be polarly covalent. As a result, there is no contribution of ionic structure of A positive, B negative, assuming B is more electronegative than A, in addition to poor covalent AB structure. Second is Mulliken concept of electronegativity. Mulliken in 1934 suggested that the tendency of an atom to compete to the shared pair of in a bond should be the average of ionization energy and electron affinity. Thus, according to Mulliken's, electronegativity of an atom is equals to ionization energy plus electronegativity divided by 2. The Mulliken value expressed in electron volt has been found to be about 2.8 times as larger as the Pauling's values. Therefore, these values are divided by 2.8 to get the Pauling's value, that's x Pauling is equals to x of Mulliken's divided by 2. Third is Allred and Rocco scale. This concept is based on the electrostatic force of attraction between an electron and its nucleus. Force of attraction is taken as the measure of its electronegativity. The force of attraction between the nucleus of the atom and its valence electron is governed by Coulomb's law, and it is given as force is equals to Z square divides by r square. E is equal to charge on electron. Z star is equal to effective nuclear charge. R is equal to mean distance from the nucleus. Fourth is Sanderson scale of electronegativity. Sanderson proposed a scale of electronegativity based on the compactness of the electron clouds around the nucleus on average electron density of an atom. The average electron density in an atom may be given as D is equal to 3Z divided by 4 pi r square. Fifth is Mulliken's and Jaffe scale. Mulliken and Jaffe have also proposed a new scale which takes into account the role of hybridization while calculating the electronegativity based on ionization energy and electron affinity. However, it has been not discussed in the present text. Factors affecting the electronegativity, and the first is oxidation state. The electronegativity of an atom varies from one bonding state to another depending upon the oxidation state of an atom of the molecule. In general, the electronegative increase as the positive oxidation state of an atom increase. This is obvious because with the increase in positive oxidation state, the tendency to attract the electron will increase. For example, Pauling electronegative value for is 1.62, whereas it's about 2.044 Ti third. Some common examples are given. Second is the type of hybridization. The type of hybridization also affects the electronegativity of an atom. We have learned the s orbital are nearer to the nucleus than p, d and f orbital because of their high penetration power. Therefore, s orbital will have greater electron attracting power or electronegativity. In other words, the electronegativity increases with increased s character of the hybrid orbitals. This can be easily illustrated by taking the example of carbon. The s character increases in order to CH4, C2H4, C2S2, and the electronegativity of carbon in this compound are also increases. Similarly, for nitrogen atom, the value of the electronegativity are 3.68, 3.94 and 4.67 or sp3, sp2 and sp hybridization respectively. Third is nature of the substituents. The electronegativity of group varies with the nature of the substituent. This is due to the inductive effect of the substituents group. In these cases, the electronegativity of these groups will be electronegativity of carbon as it is adjusted by the absence of substituents. These values are based on dipole moment, atomic electronegativity, and kinetic data. Periodic variation of electronegativity. The electronegativity generally increases on moving across a period from left to right. This is primarily due to increase in atomic size and increase in effective nuclear charge. As an effect of increase in effective nuclear charge, the attraction of the electron increases. The electronegativity generally decreases from top to bottom in a group as atomic size increases and the bonding electron become away from the nucleus. Thus, the alkali metal or group 1 have the lowest electronegativity and the halogens of group 7th have the highest electronegativity. Further inspection of table 2.14 shows that the known metals on the right hand side of the periodic table have high electronegativities while the other and the left hand side have low electronegativities. In general, as an approximation, elements with electronegativity 2.0 or greater are known metals, while those electronegativity less than 2.0 are metals. It's clear from the table 14 that the electronegativity generally increases on moving across a period from left to right and decreases on moving down a group. So that's all of our chapter. Thank you very much.